So is this these simulations with 50-50?
Hmm?
Are these simulations with?
These aren't simulations. These are just these aren't even simulations.
Numerical solution.
Numerical solution.
These aren't even numerical. These are just simply plots. I think it's for 50-50, okay? I think it's for 50-50. You just have to look back because it's a long time since these were drawn out. But just simply of these energy levels.
Right. Yes,
It's
that's what
not
I mean.
numerics, it's just
Oh, I
simply
see. So you don't
algebraic
right,
curves.
right,
And I
right,
asked
okay.
a master's student who was
Right.
doing a master's, okay?
But-
Jawad
but-
Rashid and my TA from my PD course, Marina Gruz, to plot this out. It's MATLAB.
Right, and
Okay.
the energy, of course, is dependent upon the concentration, the relative concentration.
Right.
And so if we change that, those curves would be moved.
Not so much as, I have to flip back a few slides. Okay, I'm
Yeah.
so great at flipping, okay? But the idea we have here, these are plots of E plus minus, okay? E11, E12, E21, and E22. Some of the above don't depend on the mean concentration, okay? So some of them aren't dependent, okay?
Okay.
And two of them are, okay? So some of this is more robust than you might think, okay? But for those which do depend, okay, it's with mean concentration to 0. One could also do a 3D plot in the other direction, but already it shows that it's only partially indicative. Okay? And I thank Jawad Rashid and Marina Gruz for undertaking the numerical plots from the MATLAB and dealing with the logarithmic terms, which turned out to be a bit more challenging than we would guess. Okay, so here are sort of further questions. And then, okay, are there really upper bounds for all times t greater than 0? Are there really some hidden temporal gaps when you don't have upper bounds? Is there some waiting time for these upper bounds to hold? Okay. Can the coefficients in these upper bounds really be calculated? The coefficients depend on these set of parameters. These parameters are in some domain. It looks like calculus, but it's a bit messy. Okay. Can the transition times be calculated and predicted? They look like they could, but are those real? Okay. One really has to take the lower envelope of all these to know what the real predictions are, quote unquote. Okay. And then is the initial energy calculable? That's actually calculable. So that's an easy one. And can the predictions be correlated with numerical calculations and experiments? Okay, and that's sort of a, okay. So in the Cahn-Hilliard framework, this was a bit difficult to answer in full. So we concentrated on in the deep quench obstacle problem, okay? And this is this, here we are, okay? So in order to get fuller answers, we went to a simpler problem, which is the deep quench obstacle problem with constant mobility. N is just simply equal to 1. The obstacle problem means that U has to be constrained to lie between -1 and 1. And this was proposed by two physicists, Ono and Puri, and studied by Blowy and Elliott. It was Blowy's thesis. And then we also look in parallel at the deep quench obstacle problem with degenerate mobility, which is what was obtained by just simply taking the temperature equal to 0 in the degenerate Cahn-Hilliard equation, which we saw some slides back. Okay. And so this is this object that we're looking at all the time. Okay, this S of t. Okay, that's this LR norm appropriately weighted. And then we want to look at these distinguished times when the energy is above 1/2, above 1 minus the mean concentration over 2. And we have to look at what happens with these R and thetas, which appear in all these bounds. They lie in this region lambda, which is bounded by some 3 curves, okay? So one is looking at some r and theta lying in some region gamma, and this region gamma, okay, it looks like something of this sort, with phi is equal to 1 here, phi is equal to 1 plus alpha, 3 plus alpha here, here r is equal to 3 plus alpha, and here r is equal to 1 plus alpha. Okay, so this is this region gamma, lambda, and different points give you different upper bounds, and one wants to sort of explore this region and understand where you get the best upper bound given everything else which is happening. So what happens is that for the deep quench obstacle problem, the lemmas from before, which looked sort of messy and long, had this A and this B1 and this B2, all get simpler in this context. One just has these two terms on the right, okay, on the first one, which gives you can get that at all times either E is bigger than the 1 plus U bar squared over 2, or it's less than this quantity. And if it's less than, then you already know that EL is bounded from below. Okay, and the two differential inequalities, they now have just one form for the constant mobility, and for the degenerate mobility, it's just two different possibilities. And the third lemma is as before. It terms that you can get rid of the temporal gaps, okay, but the upper bounds that you get are clearly not optimal. Meaning that there has to, okay, Y in particular, if you just write out what we get things which look roughly of the sort, you get something of this, and then you get something of this form there, and it's clear that if you just simply jump from something, you jump from here to there, it's not quite clear what you're supposed to do in the trend. It can't be that that was optimal. Something has to be. Intuition gives you that the real upper bound has to be some convex envelope or something of the sort of the above, and not some. It's obvious, but it's giving you at all times an upper bound. So you get an upper bound at all times, okay? And this is the nature of the upper bound. For the upper bound to be valid, okay, it has to be positive because you're bounding from, okay? And so it turns out that there's some waiting time for it to be positive. The waiting time can be made arbitrarily small. These bounds have a unique, each bound has a unique minima, okay? The unique minima is some multiple of the waiting time. As t goes to infinity, in fact, you can demonstrate that the coefficient, as t goes to infinity, this term becomes irrelevant. This is the term you have to worry about, and then you can actually bound this term, which comes out to be here, that you can bound that from above by 1. So that really gives you this, in the end, this t to the 1/4, or something, or t to the 1/3, as t goes to infinity. So you rederive the exact bounds, the same bounds as before, and you get something in the middle that's not quite so clear. But then you want to know exactly what bounds are you getting at finite times. So you can ask yourself, okay, you can go to the parameter region, which is roughly, okay, in the constant mobility case, it's along this whole region. For the, okay, if you're looking at these C bounds, you've got to look over here, okay? And then it turns out that when you approach this parameter limit, in point of fact, in order to get a bound instead of 1 in terms of 2 as an upper bound, constant factor above, then you have to look at times greater than some time t tilde, where t tilde, unfortunately, goes off to infinity as the waiting time goes to 0. So if you want to get a different bound, you've got to go a bit away from the bound, wait a little bit longer, and then you've got a bound which has a coefficient which is a little bit better sooner. but what the convex envelope of this all really is a different, is a somewhat involved. Okay, you get some indications of what transition times could be. Those were in these energy plots from before. And then we had these distinguishing between E above or below 1/2, and we were distinguishing between E above or below and 1 minus U bar squared over 2. And then is this something easy to realize or not? So you look at initial conditions, say, of the nature of what we discussed early on, a perturbation of a uniform state, okay? So you take a perturbation of a uniform state, you plug that into the formula for the energy, and you get out that if that's your initial state, then in fact the energy has a leading order term independent of the small perturbation, just the mean concentration. And then the second term depends on the small perturbation. So if that's your initial energy, then you know that as long as the U bar is not equal to 0 and A is sufficiently small, you're already below this 1/2, and you know you can only go further down below it. Okay? And also, if that's what your initial conditions look like, being below the value on the right doesn't look like an impossible situation to realize in experiment or in numerics or for the system itself. So we got to this point, and the question, what can you really make out of all this? One can work more and more, but it's quite clear that this is in itself not going to give the full picture. So Lubo Banash and Robert Nirenberg had been working on various degenerate parabolic equations in any case, so it was quite within the framework of, I changed where I have to, there's a second half to the, okay? So
pictures?
Yeah, I get to the pictures, okay? How do I get to that? First is okay? So I have to, okay, get to the pictures, okay? And anybody who doesn't see all the pictures, I can send them the pictures, because, where are, here, pictures, okay? So this is, and I hit on this, where do I, okay, the pictures should come up, okay, hopefully the pictures come up, okay. So here I just, how do I scroll? Is that readable? Can I make it larger? Okay, we don't have to make it larger. Okay, we'll get directly to the pictures, okay? Because the first is an existence theorem, the second is just saying we're trying to focus on linear resumed saturation and coursing. A lot of people have looked at this structure function, including Joel Lieber. Okay, he put in many years, but not exactly in the context we're looking at. Okay? And then the energy function, if you can bound it from below, you can look at the gamma limit. You know that if everything is well saturated out, okay, it should roughly behave like this middle line there. Okay, E is approximately equal to 1 minus half of 1 minus S. And then you can define sort of a measure of the gamma limit. G is equal to E minus 1/2 this 1 minus S, the saturation. And that gives an additional benchmark for saturation. So we're defining different benchmarks for saturation. Okay, 0.5, okay, that's based on this LR norm that has been described in the theory. But while we're going to run this, instead of just looking at this, okay, we also said we're going to look at this different benchmarks. We'll also use this CHOMP, okay, software were developed by Constantine and colleagues, okay. So we also look at all of that, okay, and throw that in while we're doing the runs, okay. This one's undertaken a lot of actual work in addition to the, okay, undertaken by Rubobanash now in area 1. And this is just describing the finite element method used for undertaking this. I can give this to anyone who wants. Okay. And then, okay, this is just we're taking random initial data, which is a perturbation of a spatially homogeneous state. And in order to reduce noise effects, we're doing a lot of independent simulations, okay? With the same amplitude, but different initial conditions. Hopefully, that doesn't look so bad. You can see, here it looks okay. You can see the first one, coarsening, in the constant mobility case. In the second one, what's happening with this? No, it's not going to help. Okay. Okay, it means that my time is up and Duron is right here. Okay. But I'll run through this in 2 seconds, okay? In the left, you can see this 1 over e. It should really be an integral average, but this is just 1 over e. And then you can see sort of constant, a sharp transition, and then these 2 branches like that, that's your coarsening, okay? And the upper branch is constant mobility, the lower branch is degenerate mobility. On the right, that's your saturation. You wait some amount of time, no saturation, and then there it goes, it starts to saturate, but you have this very sharp transition, and it saturates. Nobody quite heard out what exactly this sharp transition. Eric was telling me that you'd seen something similar.
Yeah.
But I'd never seen this, and Bob Cohen said yesterday he'd never seen it, I'd never. But in any case, this is a slightly different context, and it's of interest to compare the pictures. Here we have Betty numbers. Okay, so what's happening with the Betty numbers? You've got this very sharp initial decay in the Betty numbers. The upper curve is the Betty number 0, the lower curve is the Betty number 1, okay? And the upper curve is always the degenerate mobility because it's losing components more slowly, okay? And the lower one is always the constant, okay? And you can see this initial decay and in fact non-monotonicity, but relatively plateau regions, okay? So this is our experimental mathematics here, okay? And then there's something similar, okay? We're just testing it left and right for, this is with mean concentration 0, okay? And looking once with Betty numbers based on above 0 and once based below, just to see they should come out the same, okay? And then we're looking at internal components and boundary components, okay? So you can see that the internal components roughly behave like B0, but the boundary components, they're doing something else on a completely different time scale, okay? And plus above and below.
So these are all 2-dimensional.
These are 2-dimensional. If we could explain the 3-dimensional, that's tomorrow.
Yeah, because
Okay.
some group, I forgot his name, Rohr, at Carnegie Mellon, material science guy. I want to say Rohr, but not as
Rohrer? There's Rohrer, but I don't know that he's done this, but I can.
There's somebody who's
I
done
know
large-scale
Rohrer.
3D simulations looking for the Betty numbers, and they don't see this kind of plateau for the 3D.
I'll call Rohrer tomorrow.
I don't remember if it's Rohr.
Yeah, I don't think it's Rohrer, but I'd be
Okay.
happy. I can
Yeah.
ask David Kinderleiter who
Okay.
would know, or
Okay.
Shlomi Tassa.
Okay.
Okay, but thanks for because I'm
I think it
looking.
appeared in
Actima?
Act material, yeah.
Oh, okay, Actima. Okay. In any case, we just run through this quickly. Okay, here this is for different mean concentrations. Okay, and you can see some transition at when they're about on top when you was just off 0, the 50-50, a bit away from that, you see something else happening. That's sort of not new, that was known, but even in this easy context, it was known. And then here we define something called crossover times. And, okay, and that's if you look at this G, which I defined before, okay, which is this E minus 1/2, 1 minus, you're correct. You see this unique minima, and the unique minima goes to the left as the concentration goes up. In the constant mobility case, it goes to the right in the degenerate. And here we have the number of internal components over the whole number of components. And that also changes drastically after saturation. So there's lots of different things to try and explain. And here we go through, okay, we ignore this a bit. One is changing what happens. Just to double check, you change the initial amplitude, what happens. And here this 21, that's comparing with the t to the 1/3 and t to the 1/4. Okay, so for the constant mobility case, u is equal to 0. That's right on line. For the degenerate, you wait a little bit. And here I rather suspected, that's why I didn't, this is, okay, these are, I won't, this is the structure function business. And here just, I'm not quite sure what the conclusions are. And that's also multiple, I just put this in. That's why I was a bit, it's not too clear. I should, I'll send it to Joel and ask him what he thinks. You see, it's good and not so good. The conjecture is that it should have some form. It does and it doesn't. Duron is correct. Okay. The time is up, and I also wanted to, this is the last slide. I thank you all. There's many additional things we'd like to answer. We were certainly aided and being aided by experimental mathematics.
Thank you very much. I will be glad to answer questions in private, and if you'd like to join us for dinner,